let's go. And if you look at hole number 2, you guys will notice that you guys also orthographic sketching. So similar to what you guys did, you are gonna create a front, top, and side view. I think is this a full scale? Yes, full scale. What does full scale means? Do a little review if you don't know what full scale means. I'm gonna put this guy over here. Do kicks on the side. Okay, so quick. What do I mean with full scale? Take it off. It will expand so you guys could see it. Usually, you guys probably seen a bunch of drawings people go and people draw, right? And sometimes you have big objects, little objects that you gotta represent on a piece of paper. So later on, whatever you get to design gets to be manufactured somewhere else. So think of it like a piece of paper, right? Just like your paper on engineering paper. And sometimes you guys gotta put big things. Let's put a bat. Sort of a bat configuration. And sometimes you gotta put small things into the paper. The coin, when you put it on the paper, most likely you want to make it bigger, right? You want to grab this guy, you want to make it bigger. So my coin looks like this. And you do that using a scale. And then if you have a bat, and actually let me make bat bigger. Let's see, let me bat this like this. And you want to put the bat inside of the paper, you most likely the bat, if you want to draw it the same size, it will not fit. So you need to make it smaller, right? So let's say I make the bat about this. Usually on the papers, you have a portion somewhere in there that you call out a scale on both of them. Okay, that scale, all it is a factor that either increases the size or reduces the size. For example, let's say that this guy is 24 inches. It's probably not. Let's say this guy is 24 inches, and I want to make sure that when I put it on the paper, and assuming that my paper is larger than 12 inches, I am grabbing the real life, let's call it real life, and I'm putting it into a paper size, right? So I got real life, and I put it in the paper size, and what I have done is I have reduced real life into paper size. So this is what you would measure if you were to get a ruler, right? And then again, this is what you would measure if you were to get a tape measure. This is the dimension on real life. This is what you drew it at. So as you guys could see, I have reduced the real life to half the size, okay? So the way you represent this, can represent this as 1 equals to 2. The left side is what we call the paper, and the right side is what we call it the real life. Let me explain you what it says. For every unit on the paper, you will get 2 units in real life. So if I measure 1 inch on the paper, will signify 2 inches in real life. In this case, I measure 12 inches on the paper, which signifies 24 inches in real life. So double, right? That's why sometimes you will call this guy half scale. And the reason why you call it half scale, because I got the real life and I half scale it. Okay. And if you were to do 1 to 4, you will call this guy a quarter scale. And what I have done, I have scaled down the real life to a quarter of its size. That's pretty much what it means. Sometimes, not all the time, you have features that are really small and you want to make them big. And the way you make them big is you make the paper big, right? Remember, the left side is the paper, the right side is the real life. So I have made the paper big. Sometimes you will see this guy as 1 to 1/10. A little bit of algebra, right? But it's pretty much what is happening. I got the paper, I made it bigger so I can represent the real life that is small. Boom. That's what it means when I go and I say, hey, if I were to tell you, hey, give me a full scale, this means full scale means you draw it such that whatever is on the real life is the same on the paper, right? Now, if I were to tell you half scale, that means you half it. If I were to tell you 1 to 2, that means you half it. Whatever is in real life, you half of it. We will most likely talk about that later. So you guys are going to do a full scale. You guys are not going to add any dimensions. You don't know how to do it properly yet. And then you guys will notice that it has a bunch of whole callouts. You guys cannot do the whole callouts until we cover the lecture, and then after we call out how you represent them. And you might be able to start working on it. Otherwise, you should be able to create the front, the top, and the side view without any holes. And that's pretty much your assignment number 2. And then whenever we meet next time, we'll talk briefly on how it's supposed to look, and then you guys get to do it. Okay. All right. Let's talk. Talk about hole callouts. Okay. So if you guys see these holes, this is meant to represent the holes. This guy, what you guys see here, this is the top view looking from the top of a block. And then somewhere in there, it has a bunch of hidden lines which represents that there is a hole. You guys also will notice that there's a bunch of symbols representing each of these holes. And those symbols, this number represents the hole callout. That's how you call it out. When we use the 3D modeling software, we're going to be using a hole, and how we set up the hole properties will allow for the program to properly describe the hole in the drawing. So it is important that you guys understand the holes, how they look. Let's talk about the first one. Let me get some smart water. The first one is called the true hole. And what do I call it the true hole? Because it's a hole that goes through. That's why we call it the true hole. Let me make this guy, put it somewhere there. Make it slightly smaller. Okay. As you guys could see, here I have a piece of plate, like a plate, right? And within the plate, have a hole. So we call it, in this hole, by the way, it goes all the way through. So that's why you call it true hole, because it goes all the way through. Once, how do you make a true hole? You go and you get yourself a drill bit. This is what we call it, a drill bit. And as you guys will notice, this drill bit has grooves. If you guys ever done a hole, what you would do, and this guy is not a metal bit, okay? Imagine this is good. What you would do is you would most likely mark it because you want to know what it is, right? And then you will go put this guy most likely perpendicular. You want to make a hole sideways, right? You most likely will put it perpendicular. And then you will start moving the spindle, right? And the spindle will start moving in, and it will start eventually making the hole. And chips, this residue will start grasping within these grooves, and then will be pulling out outside on the surface of your piece of wood, all right? That is the reason why you have these grooves, right? So when you start extracting the material starts grasping, going around, and eventually they come out. This is what we call a true hole. The way we pull out a true hole on the drawing. Well, first of all, you gotta know what it is, the true hole. And let's say that this is your visible line, right? Because that's when you see the hole. And then you also want to have your center marks, so they're nice and thin. You go towards the center. First you go what it is, right? And what you're trying to tell is going towards the center of the hole. Move away along the same center line, along the same line. Move away, and then make a little shoulder, which is about 1/8 of an inch. And then you put this symbol. This symbol here is called the diameter symbol. Diameter. If you don't know what is diameter, the diameter is this distance, right? It's diameter. In our case, when you go make the hole, you want to get yourself a drill bit that it has the size of the hole that you want to make. Okay. The next thing you guys will notice that it has the size. It's called this like 1/2 inch diameter. Okay. You guys will notice that it doesn't have a 0 in the front. So no leading zeros for imperial system. For US system, right? So inches. Then you will tell it if this hole is going to be a blind hole or this hole is going to be a true hole. True hole means it goes all the way through. So if I go and I put through, it's automatically telling me that my hole is going to go all the way through. Okay. Now, little quick review. If you guys don't never use a chalk and a spindle, this is what we call it a hand drill. That's manual hand drill. Sometimes you guys probably have seen something that they call it a mill. A mill looks like this, right? Or maybe you just have a machine that makes holes. So what it spins the motor per se. This is what we call it the spindle, because it spins, right? And it has a certain revolutions per minute. Within the spindle, I don't know if you guys can see there is a hole. This has a little, sorry for the light. The hole in there has like a grasping thing. The grasping thing is what we call it the chocks. So the chock grasp the chocks. As I move the spindle, the chocks close or they open. You guys will notice that I have my let's share this. Well, I'll show you. You guys will notice that your drill bit has certain areas that are flat, and that's where the chock is meant to close and grasp it, right? You don't grasp on the flutes. So you grasp on the flutes, you want to mess them up, and then when your drill bit will not be good. So the way you use a manual one, which will be similar to the one, some people what they do is they hold it and then they twist it. That thing takes forever. So the way I usually like to do this, you guys will notice it has two buttons. One is going towards reverse and one is going towards forwards. And then you have a button here that allows you to activate it, right? Activate it. In my case, I have a 20-volt battery. That is what gives the power. Then when you remove it, you press on this, squish it up, and then move it out. You want to put it back in, squeeze it a little bit, stick it in, push it back. Okay? So press the button, go forward. Press the other button, go backwards. Okay? Forward. Now, in order for us to open the chocks, you hold the spindle, put it on reverse, and you hold your let's call it the spindle with 2 fingers. And don't put a lot of pressure, just barely touch on it. And I want you guys to notice what happened to the spindle, okay? So I'm gonna go. It opened up when I went reverse. If I go and I go the other way, I go forwards and I press the start button, right? You guys will notice the chock close. Really easy. Boom, open. You open the chock. You grab your drill bit. You stick it there. And then when you grab your drill bit, don't put your fingers in the flutes. And also, don't hold it too hard. You don't need it. You don't need to hold it too hard. If you go and you put your fingers on the flutes, as this guy spins, it's going to cut you. So what you do is you put your fingers on the shank. What's the shank? The shank is the part that doesn't have any flutes. So you put it there, and then you go, you hold it. Right now it's open. I'm going to hold it from the spindle and the shank slightly. I don't want to go too strong. And then I'm going to go forward, hold it, let it spin. It's done. When I open it, go backwards, hold the spindle, boom. Forwards, backwards. Okay, easy peasy. If you guys ever want to build something and let you use the tools, as long as I do it properly, I'll let you do it. Okay, so you go and you get yourself, go to online. You can go to a hardware store and you get yourself a bunch of drill bits. The way you get the drill bits, usually you don't want to buy drill bits alone because they're expensive. You just buy one at a time. You want to get yourself a drill bit set. In my case, they're made of titanium. And then when you go and you open the drill set, this guy, the other way. Come on. There we go. When you open the drill set, it's going to have, especially the imperial, right? So we're doing inches. You guys will notice that it will be on fractions. So these numbers that you guys see here, those are the diameters. For example, here I have the 1/2 inch, and here I got the 3/8 of an inch, and so forth. Those are the diameters. These diameters. So when you go and you get yourself a drill bit, you're buying them by the diameter. Again, you might want to get yourself a set. Buying a drill bit by itself is usually expensive. I don't know why they sell them more expensive like that. Now, if you guys were to have a special case where you went and you got your set, but maybe you want to have a special hole that is not part of the set, you are going to have to most likely buy a custom. And when you go and you buy yourself your drill bit, the increment size between drill bits to drill bits are going to be 64ths of an inch, 1/64th. So you got 1/16. If you have that, you will get 1/32. If you have that, you will get 1/64. So really little small increments. If you were to put that in the calculator, 1/64 is 16,000ths of an inch. So really, really small. Okay, so you go and you grab your drills and you make your through hole. Sometimes you might need more accuracy than 1/64 because you want to make sure that maybe you have a situation when you're making the hole that you want to make an interference feed. What I mean with interference feed, I don't know if you guys can see here. This guy used to be a hole, and then I put a pin. and then I went and I put the pin into some interference pin, like a push fit, right? Now this guy is not coming out nowhere, right? So that's this guy's supposed to be a little bit bigger than this one. The way you make it happen, you warm up this one, you heat it up so it expands to thermal expansion. Grab this guy and push it, and once this guy solidifies, then it will come out. That's what you do. But you guys notice interference fit. At this point of time, when you're doing interference fit, you want to have really good precision, really high accuracy, really high small changes. And the way you do it, you get yourself a reamer. What's a reamer? Okay, so let me see if I can show you the drill bit and the reamer. What's the difference? Okay, this one is the drill bit. This one is the reamer. As you guys will notice, the reamer doesn't have these grooves. So if you want to ream something, you first drill it and get it to the size really close to what you want. And then remember, the reason why we use the reamer is because we need accuracy. So we're going to have second operation, and the second operation will give me the accuracy. Now, I told you that you can go get yourself a drill bit, and the drill bit are usually 64ths of an inch. If you go in yours, and again, it's 16,000, right? Points, increments, 0.016. If you get yourself a reamer, and I can go online because you need a special reamer, you can get increments on the reamer up to 2 10,000ths. So 0.0002. As you guys could see, this is a two-way process. First, you make the drill. First, you drill the hole, and then you get yourself a reamer to account for the special size circumstances. Maybe you need a special precision, and then you use the reamer later. Now, when you go, you use a reamer. It's also like you need accuracy, right? And you're gonna have to get yourself a custom reamer to be able to make that hole. So, more operations means more time for the machinist or for manufacturing, which means more money. So you only use reamers when you really need it. Okay, so review. We have a hole. You call it out with the diameter. This guy's telling me the diameter size. Even inch drawings or imperial units, you don't put the 0. If it was all the way, you call it through. This guy's calling out the size. You're going to have to find out what is going to be the size of the diameter. If the diameter is supposed to be like super accurate and it's a special size that is not part of your regular drill sizes, or a special tolerance, special accuracy for a special kind of fit, you might want to get yourself a reamer if you need it. The through says you guys you go all the way through. I mean, you make a hole all the way through. Then you also have something that is not the through. That means it goes not all the way through. So if I were to go and I were to look at the hole, so make a 3D hole. In this case, let's say that I make a hole, but it doesn't go all the way through. It goes somewhere in the middle, right? Let's say the hole goes somewhere there, right? Well, if you guys were to look from the top, you cannot see the depth. You cannot see that it goes all the way through. They call this guy the blind holes. I don't know. Blindly, you cannot see how much depth that is. Okay. So if you have a blind hole, that means you need to actually tell it how much depth it has. And then when you go and you tell it how much depth it has, instead of calling it through, you will call that the diameter. You will call it a half. And then you will give it this symbol. This symbol means it doesn't go all the way through, it actually has a certain depth. And then you tell it the depth. The depth, in this case, is 1 1/8. And that will be the effective depth. So the effective depth is, if I were to have my drill bit, the effective depth will be up to this point. Right there, okay? So I will make the things, again, this guy is 1.12, which is 1 1/8. And that's how you will call it out. You guys will see it here at the end. Now, in terms of drafting purposes, you are drilling it, in this case, with a drill bit. The way you will draw this little triangle on the little angle right there, you will draw it 30 degrees. 30 degrees. Okay. Let's see, what do I have here? I think we talked about everything that we need. Let's go to the next one. The next one is what we call it a counterbore. You guys will notice that you will see two things. The first thing is what we already talked about, right? First operation. First operation, it says, go get yourself a drill bit. Somebody's talking. Any questions?
I'm going to press it today, okay?
Somebody needs to mute themselves. Right?
Yeah, I'll tell them.
Viviana, mute yourself. You're mute unless you have a question, please. All right. The first part, again, is the diameter portion that go all the way through. and the second part is the second operation. So you guys will notice that the label, it looks like this, right? That's the symbol that happens right after that. This symbol means to represent a counterboard. This means counterboard, board, counterboard, with R and E. It means you go and you need to make a hole that is in addition to what you already have. It's a little closer. You're going to make a hole in addition to what you already have, and it's going to have a different diameter to represent that you're going to have a bolt, right? And then the head of the bolt is going to sit in the counterboard, okay? So this is how it would happen. I will go from the top and I will make a hole all the way through with my drill bit. And then I will go and I will get myself another bit, which is called a counterboard bit, and the counterboard bit looks like this. Looks like that, right? You guys will notice that it has these grooves to cut, not here, but here. You grab this here, you seal it on top of it, and it looks like this, right? It sits, and then you put it on top of the material and it starts moving around. Yeah, and eventually starts cutting the material until it gets to the right depth. Well, you gotta tell it the size from here to there, because you're making a new hole, and you gotta tell it how much depth are you gonna give it. And eventually when it's done, eraser. Eventually when it's done, the hole is gonna look like that. Okay? This is what we call it counterboard. So the way you will pull it out, again, it's a two-process operation. The first you will tell, hey, you know what? I want a hole. Maybe I want a hole that is through. You can also do a hole that is a blank hole, right? Give it a depth. But in my case, I'm gonna call it, I have a hole that is through, and then I wanna give it a counterboard. I gotta give it this, you gotta give it the diameter of the counterboard, right? What is this diameter of the counterboard? You have to make it bigger, right? You have to make the counterboard bigger. What size of counterboard I have? 1 1/8, 0.44. So you say you have a diameter of 1 1/8, which is this diameter, and then you got to tell it how much depth it has. In this case, I think it was 0.44, right? 0.44. So the depth here is 0.44. Boom. Do I have a, at this point of time, I can grab myself a drill bit and make the first thing. I get myself a counterboard bit. And then once I'm done, it's going to look like this. You grab now your bolt and you put it inside of it, and it's going to sit nice and flush. I don't have a counterboard bit, but I went online and I found you a couple of them. And you guys could see it. The cutting pattern, most of it is here. You also have some portions that it cuts into the oh, I know why. If it gets to have, you guys will notice it has the grooves, because sometimes when you go and you cut and something gets, instead of going downwards, these grooves allows it to go up. I remember it's trying to get the chips from the material out, and that's why these grooves do. But the cutting blades are actually in the middle, and eventually your part will sit. Your bolt. Let's so 2 operations. Again, the more operations, the more money it takes, the longer time. The next one is the spot face. And why do we need a spot face? Okay. There are going to be situations where you're going to have parts that are really complex. Let's say that I have a part that looks like, I don't know, like that. And then I have another part that looks like this, right? So one part on the top and one part on the bottom. And you want to make sure that you can go and you can put a bolt. Put a bolt like that, right? And you're like, oh shoot, man, that thing is curvy, right? So if I want to put it, my bolt is not gonna sit correctly, right? The same thing is gonna happen to the bolt. If I want to put a knot, the knot is not gonna sit correctly. So what you actually do, just like, you know what, I need to make sure the thing is flush. So I am going to create a spot face. A spot face, the only reason why you put it there is so you have a flat surface to sit on. So let's say I want to put a flat surface over there, right? Flat surface to sit on. That way I will eliminate all of these little doohickeys, right? And at this point in time, I grab my bolt, and when I make the hole, everything will sit flush. That's the whole idea of the spot face. So it really doesn't have per se a depth. The whole idea is for allow you to have something flat to sit the head of your bolt, or maybe the knot, or if you have a washer to do the same thing. That's why you have a spot face. Now, in terms of drafting purposes, the way you draft it, you will use the same symbol that you have for the counterboard. And in fact, the new standard is telling you that you gotta put the SF on the top of the counterbore. So on the counterbore symbols, if you were to write it the way you would say you have a diameter that is half an inch. Let's move this all the way through with a counterbore that has a diameter of 1.12. But since I'm not giving it any depth symbol, you're not putting this symbol. It is not a counterbore. It is just a spot face. Now, since it's a spot face, it doesn't require the depth, and the depth is going to be based on manufacturing as long as I can produce a flat surface, right? Now, in terms of drafting purposes, because I don't have a depth, the standard is for you to make the depth of the counterbore to 116 inch in terms of depth. You will grab your bolt, and it will sit flush with the part. Spot fixed. Again, in terms of symbol, I think I forgot the way the new standard tells you is that right here you better write SF. If you guys write SF or don't write SF, I don't care. I won't penalize you if you follow the old standard or the new standard. For that case, only for that case. The next one. The next one is what we call it countersink holes. What do I mean with countersink? Do I have a countersink bit? No. Okay, so sometimes you get yourself this taper head, okay, and that taper head is meant to grab the bolt, which has a taper head, and sit flush with your part. Now, in terms of wood, we don't have to worry about this because as soon as you put the screw on wood, the pressure of you screwing it into the wood will create the countersunk head depression within the wood. But in terms of metals, you need a special bit. The special bit is actually this type of bit, right? You guys will notice it looks like a little triangle. The standard for that bit is, so it measures 82 degrees standard. You will grab the bit, the same concept as before, you put it in your chalk. Instead of having a regular drill bit, it will have a countersink bit. You put it there, and you take this one out, put a new one in here, and you make the hole. Now, instead of drafting it to 90 degrees, like the one that you guys see here, right? This guy here is 82 degrees, right? Instead of drafting at 82 degrees, the way we do it, we draft it at 90 degrees. Easier, right? So you guys will notice that I have here a triangle, 45 degrees, right? This represents would be 45 degrees. Do I have a countersink bit? I don't think I have a countersink. I don't know if I have any countersink screws or bolts. Oh, by the way, what's the difference between a bolt and a screw? The bolt and the screw, the difference between the bolt and the screw, it is the application. Do you want it for a bolt? Do you want it for a screw? What does it mean, bolt and screw? Bolt and a screw means you bolt something or you screw something. So bolt something. Bolt something, you have two pieces that you gotta put together. And if you go and you put the bolt and you go all the way through, you have bolted something. Right? You have a bolt and a nut. If you have something where you may also have something that looks like this, right? So if you go and you have a big hole on the top, and then the next one, the second part on the bottom. Again, this is representing one part. So this is one part. The bottom, this is a plate. It's kind of like looking at this plate. You see it? That's one plate. I just put one plate. This is another plate. And then what I did is I imagine that I have this hole, and I chop it, and I'm looking at sideways, like this, right? That's representing the hole. So one of them, this line represents that it's being threaded, and one of them just has a hole. So if I want to put a big bolt here, it will go through it, and then it will start threading in. So I can do it in color. So this is the bolt that has a bunch of threads. Right? In this case, it's acting as a bolt in the first plate and as a screw in the second plate. One portion of my bolt, it just has the shank, which I go through this first plate. As I call it, this is the first plate, this thickness, and then it screws into the second plate. Right? So in this one, I would say you get the choice to choose if it's a bolt or screw. You can call it either way. Now, when you go and you have wood, usually you grab yourself your screw and your grab, and you get yourself your drill gun, and that thing will sit, and it has this screw, right? So you go and you put it. And in this case, the screws. That's why you just call it screw. And that's the difference between a bolt and a screw, in case you guys didn't know it. It's the application of how you use it. Okay, so remember, a countersink hole, you will have this symbol, and you're going to have to tell it the diameter of the counter bit, right? This diameter, right? And which is going to be the size of the head, right? And then you are going to have to include this just to make sure that they use a regular standard countersink bit. And you also got to tell it the diameter, right? Diameter of the countersink. Again, you guys will notice it is a two-part operation. And for every operation that you do, you gotta let it know, right? For example, you could have a half inch, instead of being true, you can tell it that it's a blank hole, so give it a depth. And then you could have given it either a counterbore, or you could have given it a spot face, or you could have given it a countersink. Now, what about if I have a bolt, but my bolt is not just a regular bolt? It is a bolt that has threads. Well, for that reason, we need to talk about threads. Okay, so this is a bolt. So they have a bolt over here. Bolt, for real bolt. Again, in my case, I'm going to use it for bolt. This is a bolt, right? This portion right here, we call it a shank. And then these guys over here are threads. You have two types of threads: external threads and internal threads. Internal threads are the threads that are internal. I want to hope that you guys can see the internal threads, and the external threads are the threads that are external. So when I go and I have internal or external threads, it will look like this. Let's first go over regular nomenclature, right? So you understand what I'm talking about. Most of the time that you go get yourself we're talking about imperial right now, right? Most of the time that you go get yourself an imperial 1-inch bolt, but you don't usually find 1-inch bolts in the hardware store. Let's call it a 1/4-inch bolt. You are going to be using the Unified National Standards, which is what we use in the United States. And the angle of this little thread is most likely going to be 60 degrees, most likely, right? Unless you have an old machine that was built back in the day, maybe this thread will not be applicable. Before they didn't have standards. Now, if you guys want to look at the bolt, the distance between crest, we call it the pitch. In other words, the crest is the little corner right there. That's the crest. The root is what's inside, right? That's the root. So the distance between one crest to the other crest is called the pitch. The thread angle, again, is always Unified National, and usually it's going to be 60 degrees. Now, the shank, again, I told you the shank is the portion that doesn't have any threads. You're going to have an external thread, and you're going to have an internal thread. Now, when you distinguish, when you're calling out the holes, you need to know what is the major and the minor diameter. The major is if I were to go from the crest, the top of it, to the other crest, squeeze it from crest to crest, that will be my major. If I were to go from the root to the root, you will have the minor. Right? Now, somewhere at the interface, when I'm grabbing a ball, for my bolts, right? And then you have a hole that also has internal thread, right? Sometimes at the interface between the bolt and the external thread and the internal thread, there is an interference where things meet with each other. Well, this guy engages into this guy, right? That's the whole idea of this guy is kind of like an interaction between surfaces. The point where these guys meet, let's say they meet somewhere there, this distance where they meet, they call the pitch. We call it the diameter, the pitch diameter. So if one will, we're not going to do this in this class, but when you call out, when you have a certain tolerance on the pitch because you have a special application, you are calling it out to the pitch. So you know, probably won't never use it, but so you know what's pitch. Okay, so important stuff. Major diameter, minor diameter. Remember, the pitch diameter is the interface, or the diameter pitch is the interface, and the distance between crest to crest is just called the pitch. Okay. I know diameter pitch and pitch look similar, but just remember one is the diameter. Now, in terms of drafting things, it is important to understand the difference of how you put it on the drawing. And I think that's where I'm going to leave this lecture today. We most likely will finish next week. If I were to go and draft it, I don't draft it like you guys see on the top. That would take me forever. So the way you draft it, and you guys are going to do it, is we use what we call the simplified thread representation. And I didn't write it, but you probably should write it. It's called the simplified thread representation. And what you guys see here, this is the representation for an external thread. So this bolt will be represented this way. And then this internal thread will be represented by these three views, depending on what you're looking at, right? Okay, so what these guys came about, how do you know which one it is? Okay, I'm gonna go and I'm gonna look at the bolt, which in this case is the external thread. This guy is somewhere but there, and bring my camera, shrink it slightly. If you were to look at a bolt, if you guys were to look at the bolt, you guys will notice that you have this external thread. And if you guys were to be looking in this direction and move it on the side, what gets seen, when you see it solid, it is the outer diameter, right? Which is the distance between the crest, right? The top of the thread. However, the inside grooves, I don't know if you can see the inside grooves, which are the roots, you don't see it. They actually look like hidden. So they look this one, and then this one is the root. And if I were to look at it from the side, let me see. That's how they represent it. Like if I were to look at the bolt from, like if I were to look for the bolt like this. And again, where did this one came about? Because remember, you have this behavior, right? I'm looking at the bolt that direction. I don't draw it like this, I draw it like this. When I'm looking at this direction of the bolt, I see only this as only the outside visible. So your major diameter will be visible while your minor will be hidden, right? I hope you guys see it. Now, we also have internal trends. We don't, not everything is about external. We also got internal. So what do we do with internal? Well, let's take a look at internal. I'm going to do the same concept. I'm going to go on the internal with my eye. Right. So for the internal, let's move this a little more. Internal. When I look at an internal, where's the bolt? When I look at an internal, you guys will notice that you have grooves, right? That groove is where these bolts are going to engage, right? See, that's why this external right there, this little thread is going to engage into the internal there, right there. Okay. So the inside of the groove is where the cut is. So let's see, grab that one. This is the external, right? Let's see, put a bolt right there. The inside of the groove, which is this one, this one is the external, has to go into the internal, right? I mean, also, the external has to, the outside diameter of this, of the thread, has to go into the outside diameter of the internal. So again, this is the bolt, this is the hole, this is the external, this is the internal thread, right? In this case, might not. So that guy has to be made into that one. Now, if I were to look at the internal thread, what I would see visible is this point and that point. In other words, the inner diameter. Remember, this guy is the outer diameter, and this guy is the inner diameter. You see it? So when I'm looking at the hole, the inner diameter is what I see visible, while the outer diameter, it gets hidden because it is, you see, the outer diameter is hidden inside of the groove. That's why you show it hidden, right? You cannot see it. You see anything? It's not that it's hidden. All right. So when you go and you represent it on the drawing, you do similar concepts. You guys will notice this is what we call it a section view. When you put it as a section view, that means you cut the hole right in the middle. So it's kind of like if I were to go and have a hole. Sorry for this, I gotta carry up. If I were to have a bolt that has a thread, right? And if I were to cut through it, and look at it from the cut, right? The thread will look like this, just like I told you. This will be the thread. All right, so that's what you guys see here on the section view that I cut it, and in this case we call it section lining. We talk about it when we look at sections. The front view, the same concept, right? The minor diameter is going to be visible because that's what you see when you see an internal thread, and the major is going to be hidden. The side view will just be both of them here. Okay, I believe that's where I'm going to leave it at. What you guys have learned today is a couple of holes, how you call out a simple hole. Either can go, it could be a through hole or it could be a blind hole. You can use a drill. So the minor is the smallest. Yes, the one that goes from the root to the root. You can use a drill bit. You can use a reamer. You need a reamer for special diameter applications. You might need a counterbore for the board to sit on. And you need a counterboard that has like a C square seated down. For the counterboard, you need to let the depth. For the spot face, you don't need to let the depth because the spot face is just for something to sit on, flush. You can also have a countersink, and that will be for my taper heads, my screws. And for that one, remember at the end, you are always gotta give it the diameter. Right? So let's say that the head looks like that, right? This is the bolt. So when you make the hole, you gotta give it the diameter. You gotta give it the diameter, and you gotta call out the angle. The standard is 82. We usually draft it at 45. The way you will call it, you will add this to the drawing. You will put the symbol. Then you will give it the diameter, which is this diameter. You will write it down right here. And then you say times 82 degrees. Don't forget to add this and this. Don't forget the symbol. Finally, we started talking about the internal threads and external threads, and I told you guys about the simplified thread representations of how you draw external threads and internal threads. Next time we meet, we will talk about how you actually properly call callouts, and we talk about also about metric threads and so forth. You are going to have a leader pointing out to the future, calling out to a hole, so I will have a callout towards the center of the hole, right, something like that. And again, don't forget your line weight, something like that. You go crazy on the line. It's better to be darker and thicker than non-thicker at all. Then you guys will also have your center marks, right? And then here you're going to have different ways of calling out this hole, right? So the first one, if I recall correctly, it was a through hole. That means that this hole is going to go all the way through. The second one, you say, you know what? Instead of making it through, I might make it a blind hole. A blind hole will say you don't go all the way through, you have a depth. And let's say in this case the depth is a 1/4 inch. And you say, okay, so that's the first one that we look at is a hole that is through or a hole that is a blind hole. We also talk about maybe you can also have a hole that it has a seat. So in that case, you are going to have 2 diameters. And again, you guys will take care of your line weight. You gotta actually hurry up. You go and you have the first operation, which in this case, let's say the first operation is making the through hole, which will be this is the through hole. And the second one, you can have a counterbore. Well, if you have a counterbore, you are going to have to tell it its diameter. Let's say the diameter is 1 inch. And if it's a counterbore, you also will have to tell it its depth. Let's say the depth is 1/4 of an inch. You can also have a spot face. If you were to have a spot face, you will repeat the same thing here. You will repeat the symbol. You will repeat this, but not depth. Right. And if you were to draft it, the way you would draft it is you will make it to 1/16 of an inch. This new standard is telling you that if you have a spot face, put SF. You can either put it or don't put it. I don't really. I'm not going to grade you to put it or not put it. Depends on the standard that you're using. You might see it like this. You might see it like this. You should be aware of both of them, though. Also, you might also have a countersink hole. And the way you do a countersink hole, you do the first operation, and then you go and you give the countersink symbol. You give it the diameter of the countersink. So say it's also 1 inch, and then you tell it by standard what is the angle of your countersink beak. Right. So this guy, the angle of the countersink beak will be 82 degrees. Boom. Right. That's a pretty good review of what we did last time. And again, if you still have questions, either ask me during lab or rewatch the video. Okay, also the other thing that we did is we started looking into thread terms because we needed to ensure how to draft it. I explained you last time which ones were the major and minor diameter, what were the pitch, what was the pitch diameter, and then we observed which one should be hidden and which one should be visible. I think that's where we left off. Let's talk about, let's see, let's talk about whole callouts. Whole callouts for threads. So we have done all of the other ones. We only need this one. So how do you call it out? Well, first of all, there are way too many threads, and I have a bunch of them here. If we have a regular thread, let's see if I can show you on the camera. This is my regular thread. The angle between if I were to go and drive through the thread, the angle of that thread is usually 60 degrees. And 60 degrees, and I can hope that you guys see the little angle right there, right? They're usually 60 degrees, and this 60 degrees is a standard for the Unified National. Unified National is the type of thread that you will see every time that you go to the hardware store. Before, however, back in the day, we didn't really have a standard. People used to go and make their own machines, and they also used to come up with their own threads until they started to normalize and standardize things. So every time that something breaks down, they don't have to go to manufacturer. They can go to the hardware store and find the same type of bolts, same type of threads. Nowadays, you will have certain threads that are standard, but will not be the ones that you find in the hardware store. For example, this one, you guys will notice that it has a different shape. This guy is type of a square thread. As you can see, you guys see how it looks like square. I also have an Acme thread, which is kind of like a paper looking like. I don't know if you guys can see it. See it there. Paper. It looks, you guys cannot see it, but it's kind of like, I think I have it better here in my, what is it? Acme. Right here, Acme. Looks like a taper. Kind of looking like you see the angle. And you guys also will notice that this guy is not 60 degrees like a regular standard. The Unified National will be the one that you will see all the time. The Whitmore was used during the Industrial Revolution when people started thinking more than they usually think now. I'm just messing with you. You also have other type of threads. I believe I showed you guys the modified square. Since to me, you also got knuckle, you got modified buttress, you got dartlet, you got the sharp B, you got the worm thread. And they all have their own use, and the use is most likely it's going to be based on the demand. For my general use, most likely it's going to be Unified National, which is the one that you see, in your regular hardware store. But anything that deals with power transmission or a lot of torque or a lot of speed, like positioning devices for a CNC machine, will be using something that allows them to have a little bit more meat, right? You see, a little bit more squarish area. And the reason is because they're taking more load. They are moving, so positioning things, and they have to be a little bit more accurate. Okay. You guys could actually look at the different type of forms. You guys have the sketches on the top, and again, you also have the use. But we are going to focus on the Unified National because it's the one that you see all the time. We kind of already started talking about the terms, but if I were to tell you what you should remember, so you can understand the regular thread representation is, you should remember what's the pitch. You should remember what is the minor diameter, the major diameter, and you should remember that the thread angle is 60 degrees for the Unified National. Now that you remember this, then it shouldn't be too bad to start reading the charts, which are based on the Unified National and the metric systems. Metric systems are similar in terms of how they look, but the way you call it out is different. So let's say how you call it out. Okay, so not this one. Let's say, do I have a call out somewhere? For call outs, no? Let's see if I can find it. I got a little cheat sheet that tells you how to call them out. Okay, we'll find it. For now, let's notice that when you go to the US system and you're looking for a thread, you might have the way usually you call it out is based on the shank. So if you go and you get yourself a bolt, if you go get yourself a caliper, you get a caliper, and you want to get yourself a bolt, and you're like, oh, I don't know how to pull this one out. Well, first of all, every time that you go to a hardware store, it's going to have the UN. actually, when you're looking for the whole callout and finding the right bolt, you will see that UN is most likely the one that you will find all the time. Then after, you're going to have a letter here right after the UN. You're going to say UNC, or you might have UNF. The C stands for coarse, and the F stands for fine. And you're like, okay, what's the difference between coarse and fine? Well, coarse, you have bigger threads, like big or chunky threads. And fine, you have fine threads. Let's suppose that this is one of my bolts with a bunch of big threads. That will be the coarse, and the fine will be like this, right? Something like that. So I give you guys a table, and this table is telling you the standard series for the unified national threads. And if you guys were to look at it, you guys will notice that below a quarter of an inch, you will have a number. So in other words, every time that you guys see and you see the thread that is number 1, number 2, number 3, number 4, they're actually talking about major diameters that are below a quarter of an inch. That way you guys could see it below a quarter of an inch. And you guys also notice that you guys have unified national coarse, unified national fine. Again, that's the difference. One, you have thicker threads. The other one, you have nice and fine threads. After a quarter, you will get increments from a quarter, all the way increments of a 16th. And somewhere after the 9/16, you will have increments of an 8th. That's how you will see these ones, most likely. And again, they also have customs. If you were to go online to find a custom thread, the smallest increments that you will ever find if you were to get a custom will be 64th of an inch, right? But most likely will be a custom, which means you're going to have to pay more. So usually you don't go and you get anything custom, because anything custom will cost money. And if you work for NASA, you got money, you are able to spend on different type of threads. But in reality, you will always be using nominal. And again, this is a nice cheat sheet because it tells you what is your nominal size, how you will pull it out, and what is your actual diameter, major diameter. Remember, you have two type of threads: unified national coarse, unified national fine. You guys will notice that you have for the fine, you have more threads, so you have a bigger number right here. Threads per inch, in this case, will be 20. So, for example, let's say that I want to cut out a bolt. Well, first, I look at the size of the bolt. So, let's say this is my shank, and I'm gonna hope you guys can see this if I can zoom in a little bit. This is my shank, right? And then in my shank, I will have a thread. And again, this is the simplified thread representation. The shank, you will go with your calipers. You can measure the shank. The shank will be usually pretty close to the thread. And you will call out the thread. Let's say call out the thread here. And let's say that this guy is about a half an inch. This is about half an inch diameter. Pretty close. So you will call it out. You will not put the diameter. The whole collars don't have a diameter. You will say a half, right? And then you will come to my chart. Actually, let's not quarter. Let's not know a half. Let's not quarter inch. A quarter, and then you will have a little dash, and then you will give you your threads per inch. Threads per inch. So if I were to measure 1 inch in length, how many threads would there be? For example, in terms of my quarter, you guys see here a quarter. For a unified national coarse, you have 20 threads per inch. For a unified national fine, you have 28 threads per inch. Let's imagine that I have 20. So I will put a 20 right here. A quarter, 20. And then I tell it, is it going to be unified national coarse? Because remember, for the coarse, I have quarter 20. That's what is the quarter here? Quarter 20. Right there. That's how you would call it. There's still more callouts to do, but for now, let's just keep it like that. That's what you use this chart for. If you were to have a metric system, you do not call out by the threads per inch. You call them out by the pitch. The pitch is the distance between peak to peak or crest to crest. You have a preferred size. See, that's preferred size. You usually the same concept. You use your preferred size. This is the way you call them out. And you can call them out by the preferred major diameter or by the preferred major pitch. Depends on whether you have a coarse thread or a fine thread. And again, this is the representation of the coarse and the fine thread. And then you are asking yourself, okay, so Professor, you're telling me that you have two different type of threads. When do we need two different type of threads? Well, let's think about it. Here I have a table, which is coming from the machining manual, which tells you that depending on your bolt, in this case, I'm looking at the quarter inch, for example, the we're doing, and I'm looking at the area, it's giving me that I have an area for the coarse thread, I have 0.0269 inches square inches. And for the fine thread, let me see what is the fine thread. I have 0.0326 square inches. So you have a little bit more area on the Unified National Fine. What's the difference? Let's think about it, okay? So I'm gonna go and I'm gonna ask you guys which one will be stronger. And I'm gonna assume that these guys are cylindrical shapes, and I am going to go and I'm gonna pull them apart with the same amount of force, but it's gonna be a force that is going to be increasing, and this is the same material. After a certain amount, the material that's the skinniest, again, both of them are the same material, and the load continues increasing until failure. The little area that I hear, the little part that's inside of it, is going to go under tensile stresses. Internally, we'll have to carry the load that I'm putting, and the one that will have the most area will be the one that will be able to support more load. Now, if we use this kind of like thinking, in terms of thinking about the threads, which I'm going to do right next to each other, this, and then I'm going to put the other one that looks like this. Something like that. Right, I went and I got them both of the areas right next to each other. This one is the Unified National Fine. Let's call it the Unified National Coarse. You guys will notice that the Unified National Coarse, if I were to look at the area in comparison to the area of the Unified National Fine, the Unified National Fine has more area. Because it has more area, it has least amount of stress applied internally. It's kind of like when you go and you apply the load, something if you were to poke yourself with a needle or with your pencil, and would be ouch. You're being stressed by the amount of area on that force. Now, if I were to apply the same force, but instead of applying it on a little point, I were to distribute the load, I will not feel the same punch. Same concept happens to the material. When I go and I apply the load, the one that has the most area will be the one that be the least of the stress. Therefore, this guy will be stronger. I will be able to restrain more stresses. This guy will be a little bit weaker. However, Unified National Coarse gets used all the time. In fact, if you were to go to the hardware store, most likely the one that you'll see available all the time will be coarse. Why? Because it's easy to install. And also because you have bigger threads, your threads will not be deteriorating over time as fast as this one. This guy, you try a couple of times, you don't do it correctly, you might tear off some of these threads and then it will be not good. And it also takes you longer, right? Longer to thread things because you have a nice, like really fine thread. And again, in terms of strength, the Unified National Force is stronger, but it takes you longer to thread. And in terms of the Unified National Coarse, is weaker, but you have it more available, and it takes you less time to thread, in, and then usually you don't mess up the threads as much. You have bigger chunks of threads. And that is the reason why I told you guys that you guys different type of threads, especially the bigger threads you use it for positional devices like CNCs. Why? Because they have more chunky threads. Do I have something here? Let me see. Sometimes I go. Again, same concept. You want to apply something in terms of tension as if you want to apply something in terms of shear. And shear means I got the top plate here and then apply a load this way, right? And I grab the bottom plate and I push it towards the right. The load will be transferred to the bolt somewhere in the middle, right? Somewhere in the middle. And I will want to shear off the bolt sideways. Like this. I'm going to have a bolt and try to see sideways. And again, same concept. You have more area, you will have a better strength. You will not be as stressed. Let me see what I wrote here. Let me see. Note the difference in area at the minor diameter and tensile stress area between the coarse and the fine threads. Fasteners with fine threads have more uncut area and are stronger, since thread fasteners typically break by pulling apart due to tension. On the other hand, fine threads are easier to cross-thread. Let me get back. The little threads are so skinny and take longer to tighten, since the pitch is smaller. The distance between peak to peaks in the thread is smaller, so it takes longer to tighten. Hopefully that makes sense. Okay, so this is the one that I was telling you guys. This is how you call them out. You have two types of system for the Unified National. Actually, you have this type of system for this type of thread, the one that has the 60 degrees. You have the Unified National, which you can call it Unified National Coarse, Unified National Fine, and you have your metric systems. If you go to the hardware store, most likely you will find these two. Okay? Let's think of the Unified National. Well, the first one is the diameter, and You usually call it out as fractions, but I have seen it call out as decimals. If you put fractions or decimal, I will not penalize. But keep in mind that you don't put a diameter, okay? No diameters in the front. Then you put a dash, and then you tell me the number of threads per inch. In our case, the example that I did before, I think it was a quarter 20. Then you call the unified national, which is the standard, is the series. And then you give a coarse or fine. Then you put another dash, and then you indicate the class of feet. So you can do class number feet 2, number 1, or number 3. The average will be class number 2. You have the loose feet and the tight feet, but the average will be number 2. You most likely, every time that you go to the hardware store, you will have the number 2. If I don't call it out or I don't tell you anything and I tell you to call it out, you will put the 2. Then you will have the A. The A indicates you have an external or an internal thread. The A indicates external. For example, this is a bolt, it's external thread, so you will put an A. If you want to have a hole that has an internal thread, you will call out a B. And then you call out the length of the thread. So for example, let's say the bolt that you have here is not across the whole length, so the whole thing is 3 inches. 3 inches of threads. You will call it out on the drawing. You have 3 inches thread. Now remember, you don't draw it like this. You draw it like I showed you before. You draw it using the unified thread representation for a external thread, external, and for an internal thread. Okay. Remember, for an external, the outside diameter, the major diameter is visible, and for an internal thread, the minor diameter is visible. And again, I explained it why last time. Keep in mind also about the line weights, right? Sure that when you guys do it, you do it right. Also, you guys also will notice that you have the metric systems. Again, same concept. You go to the hardware store, you're looking for a metric system for an M series, for an M. The M indicates that you can have metric series. And then the next number will be the diameter, millimeters, it will be the major diameter. Okay. For example, if I tell you that you have an M8, that means you have a diameter here, that is going to be 8 millimeters. Or you can have a 5 millimeters. And then right next to it, you have your pitch. Your pitch is the distance between crest to crest, peaks to peaks. While the inch system, imperial system, unified national, coarse or fine, you're calling out to the threads per inch. In the metric system, you're calling out to the distance between peak to peak. So not the whole inch, just distance between one and the other. And then right after the end, you are going to have your feet per se. For example, you guys will notice also that you have a lowercase and you have an uppercase. Most of the time that you call out a thread and internal system, you are also going to have an average feet or a medium feet. So most likely you will always see a 6. But you can also have the tie feet, you can also have the free feet. Now you guys will notice that you have a lowercase and you have an uppercase. The lowercase stands for external, which is kind of like your bolt, right? And the uppercase stands for internal, which will be like your holes when you have a hole that has an internal thread. That's how you know between you have external and internal because of the letters. And here, the one that you might want to remember is the one in the middle, right? Because most of the time you're going to have a median and an average feet. And you should have this sheet somewhere in your cheat sheet that I gave you at the beginning of the class. Okay, now you're like, I am going to put a thread. How do I do it? Well, step number 1. What do I do? Step number 1. You go get yourself a plate of aluminum, or it could be actually even wood. No, probably you cannot do it. Say a metal. In my case, I have aluminum. And most likely you need to locate where the hole is going to be. What is the space between the edge from here to there, and also maybe from the end of the plate, right? Eventually you will mark it somehow, right? Second, you're going to go get yourself your chalk, which in this case I have a manual drill, hand drill, and it has a chalk, and the chalk is grasping a drill bit. So I'm going to go and I'm going to make a hole. Okay, and I remember this hole could be true hole or it could be a blank hole that has a depth associated. Now that you go and you have the hole, you get yourself a tupper. I get myself a tupper somewhere. I don't have a tupper. Let me see if I can find one. Somebody took my tupper away. Let me see if I can find one online. What is a tupper? So let's say thread tupper. Boom. And put it there. Let me see if I go to the images so you guys can see a little bit better. So if I were to look at the thread tapper, you guys will notice, that, copy this one, copy the image somewhere, copy image, and then put it somewhere here so we can zoom. If you were to look at the thread tapper, you guys will notice that it also has the groove. So it has like a groove, just the same way that you have on the drill bits, because again, it's meant to put all the extra stuff in the middle. And then you guys also will notice that you have the shape of the thread right there. That's the shape of the thread. So as you go and you put the tapper, you grab yourself the tapper, you buy it, you put it in your chalk, which in my case I have 100, so I will put it there. I grab the tapper, I put it on top, and then I start. Eventually, once you get your tapper in, it's going to create the tabs, which is the internal threads. At this point of time, once it creates the internal threads, then I'll be able to thread in my hole. Simple as that. So you just get yourself a drill, you get yourself a tapper, put the tapper inside of the hole, and boom, done. Now, if you want to get you want to do an external thread. So again, this one was internal thread, the one that we just did. If I want to do an external thread, it's a little bit different. You get yourself something that they call it a chasing die. Why do you call it chasing die? Is because it chases. A die is just a piece of metal that you use it. It's really, really accurate, right? And they call it chasing die, chasing knot. You buy it, and it tells you the size of the thread that you want to put in there. So get yourself a shank. It's a shank. Shank is the portion that is not being threaded. Okay, so you get yourself one that doesn't have the threads. Okay, then you put this one on top of it, right? And you grab, if you wanted to do it manually, you're gonna get something like this, right? You go and you buy it, you put this one inside of it, like that. Make sure it's nice and tight, and then you tighten it, right? So that's a move. Then you grab yourself your piece of metal, right? With a shank, and just the same way that you sharpen the pencils, right? The same way that you sharpen the pencils, kind of the same concept. But instead of you moving the pencil, you hold the pencil with some type of a vise, something that doesn't allow you to move, and then you grab this guy and you go like a sharpener. And you keep on moving it, rotating it, right? That's why you will notice that it has two handles, is because it's supposed to have a lever. And then as soon as you move the lever, then you will start creating the thread. That's how you do an external thread. Eventually it will look something like this, right? And again, you buy them like that. That's how you get external or internal threads. Now, when I was explaining you about the external and internal threads, I told you first you drill it. Once you drill it, the second operation will be the tapping. So you get yourself a tapper. Now, there are two different types of tapping. You have one that you call it a regular tapper, which is the one that you guys see here, and the other one is the bottom tapper. So the regular tapper will go, the way you will tap, you will have your effective depth. Your effective tap will be this. This will be my effective tap. The bottom one is just going to take all the crap out. Now, if I want a bottom tap, which means I want to get the thread all the way to the bottom, you notice the regular tapper doesn't go all the way to the bottom. You want a bottom tap, if you want to have thread all the way to the bottom, you get yourself a bottom tapper. Regular tapper, bottom tapper. So the drill was the first operation, the regular tap will be the second operation, bottom tap will be the third operation. And the more operations you do, the more money it is. So be aware of this, how much is your design going to cost. And then you ask yourself, okay, so I want to tap because I want to put a bolt. And when I want to put the bolt is because I want the part on the top and the part on the bottom to unite, become one. And I can disassemble it later if I need to. How much should I tap into the material? Well, if you guys were to look at a regular bolt, and remember, my bolt is most likely going to be stressed and it requires to have area, right? So as it has, it's trying to putting two things together, the interface between the bolt and the nut, you need to make sure, even if you want to have just a regular bolt and screw into something, you want to know how much thread you need to put into your internal thread to be able to develop the strength of your bolt. And then usually the way you do it is you look at what you're going to be making. You don't know how long to make the thread, so you can develop the bolt strength. You go and you say, okay, so what is this diameter? Okay. Once you know this diameter, you say, okay, that's what I need of depth. If you want to have a steel, that's all you need. The diameter of this is how much your depth should be. That way you'll be able to develop the strength of the bolt. Now, when you have material that is softer, like some type of a polymer, plastic, or maybe you have a soft metal like zinc or aluminum, you actually have to increase the depth of the top, right? So again, you come over here, you're like, okay, so what is the diameter, right? What's the diameter? Oh, pues that's how much I need to make here, right? In terms of my thread. But if you have a softer material, you will have to say, you know what, I am going to make that number bigger, my tapper, I'm going to make it bigger, and usually the distance is going to be about 1.5 the diameter of the bolt to about 2 times the diameter of the bolt. That way you'll be able to develop the strength of the bolt. Hopefully that makes sense. When you go and you get yourself a thread, either external or internal, you also need to know if it's going to be a left hand or a right hand. How do I know if I have a left hand or a right hand? Well, you grab yourself your bolt, and it's kind of like a little bit hard to say, and you look at your thumb, okay, your thumb. And I'm going to hope that you guys could see that my threads are kind of like inclined a little bit towards the left side, okay? So in my case, I have a right hand, and my right hand is pointing toward my right thumb. So this guy is a right hand thread. Hopefully that makes sense. And if I were to have a thread that was pointing on the opposite side, and my thumb on my left hand follows that direction, that would be a left hand. So here I got a thumb, here I got the direction. So most of the time, just like the same way that we have average feet on the threads or medium feet, most of the time we always have right hands. In fact, if you go to the hardware store, I'm gonna say all of them, I don't think they even sell left hands, are gonna be right hand threads. And you guys are thinking, okay, so what do I need right hand and left hand? Right hand is righty tighty, lefty loosey. You've seen it before, right? That's what I usually use. For the left hands, though, they have a different type of rotation. You will see this for things that is when you go and they are going into operation, they actually get tightened even more. For example, if you guys ever were to use a table saw and you're cutting wood, the way it is set up for the blade, it has a left hand thread that every time that it cuts something, it engages even more. So it will not get loose. And you don't want a table saw, I mean, it's a blade that cuts. They call it table because it's a table. You put a piece of wood and then you slide it, and it has a blade that is moving like this all the time. And you want the thread never to get loose, otherwise you will have a flimsy blade that might go and kill you. That's why you have the left. You might also use it for tension rods. These tension rods are used for applied tension. You will see here, this is a metal building. They have double rods. You also will see them on the top of the roof. And the way somewhere in the middle, they have a turnbuckle. And the reason why the turnbuckle is so that you apply the tension on the rods. The turnbuckles, they're a special type of threads because you have a left hand and you have a right hand. So one is left, one is right. Let me see if I can show you one. You guys can see it. My camera is messing up, it's lagging. All right, so hopefully you guys can see that it's in there. My thing is lagging. But in there, you guys will notice that you have and again, if you guys want to have this, take a look at this, I have it on the left. You have a left hand and a right hand. And the beauty of it is that if you move the left hand and the rods, you want to rotate them, they will go close towards each other. And if you move it on the opposite side, they will separate from each other. That means when I go and I move the turnbuckle towards one direction, they can get close to each other, and then will apply a higher tension on the rods, keeping the tension on the cable. That's why the reason why you have them there, right? Why you have them there is because if you want to have a building and you want to apply a load, the building is going to want to rock this way. But you have a cable that does not allow it to rock. So when this guy wants to come over here and start deflecting, the cable will go into tension. And when it wants to reflect the other way, the other cable will go into tension. That's why you have these effects. Hopefully that makes sense. Final, multi-starters. That will be a good introduction. I mean, there are many things to talk about this, but very good introduction. You have a multi-start, and a single start, and a double start, a triple start, and the double, the triple, and the quadruple, we call it multi-start. It's going to call it. But you can call it single start, double start, triple start. What all it means is that if you guys were to go and you want to put a rope, right? And one of the ropes were to start, you see, I go over here and I look at the end of this guy. And were to look at that at the end, one of them will have a little portion where my thread will start rolling up, right? And the other side, which is this one, coming from the top, I will have two little portions where my thread will start rolling up. So you guys will notice here I got the first row, and then right next to it you have the second row. Where is the second row? That one. That is the second row. And you're like, okay, so one is a single star, one is double star. What is the difference? The reason why you use single, double stars, triple stars, quadruple stars is because you want the things to engage faster. When you have a single star, it will not be as fast as a double star. And again, think about it like when you have a water bottle, right? When you have a water bottle, if I want the bolt or if I want the cap to engage into the thread, if I want to have a single star, I will have to rotate the cap 360 degrees to be able to engage it. But if I will have double stars, I will not have to turn the cap 360 degrees. Maybe I have to rotate it 180 degrees, right? Now, if this guy will were to have 3 stars or quadruple stars, instead of me rotating 360, maybe I just have to rotate it 90 degrees. That is the difference between different type of stars. It allows you to screw faster. So let me see if I can. Right. Multi-star screws start tightening up with less than a turn and advance as fast while you're tightening. The leg hand and multi-star screws are rarely, if ever, used in fasteners. The one that, remember, the regular, most of the threads are going to be average fits, they're going to be single star, and they're going to be right hand. All of them, pretty much all of them. The majority that you will go find out everywhere else, most likely are going to be coarse, because they're cheaper too, by the way. Unified National Coarse, they're usually cheaper. You will see not Unified National Coarse, but you might also see fine, and you will see the metric systems. You will not see left hand, you might not see multi-star, but it's a good idea that you should be aware of what it is. Remember, you have Unified National, but there are other type of threads, and the more squarish looking line is because you are going to be experiencing motion. In terms of your homework, when you can start working, you are going to create your orthographic views, but now you have a couple of holes. And in this case, you have a half, 13 UNC, 2B, 3X. So the 3X, by the way, is wrong. There's 3X should be in front. You got 3 of them. So a half an inch is the diameter for the major diameter. 13 is that you have 13 threads per inch. And then Unified National Coarse is that you have threads that are thicker. And 2 is average fit. B is the internal thread. When you go and you draw it, you don't have to actually go look in the book and try to find out exactly what is the diameter, especially on the minor diameter, right? Because you guys are drafting it with paper, with hand sketching, right? So you will never get that accurate. So when you go and you make your major diameter, make it to half an inch, and when you make your minor diameter, just try to make it smaller. Make sure you have a nice line weight, line thickness. Remember, none of the dimensions. This is not a dimension in drawing. Just come up with the views. All right. I think that's.